Hello and welcome to 12th lecture of course on data enabled tribological engineering from experiments to predictive model. Topic of this lecture is solid lubrication. We have covered a number of topics on lubrication. Now if I refer this paper 1992 about the solid lubrication process, Singer has mentioned about the solid lubrication processes, and he has mentioned a number of solid lubricants or number of material which can act as a solid lubricant. It can be lamellar solids like MS2, graphene, which is our very known. Oxides also can work. Halides, chalcogenides, soft metal, which we have been utilizing for the centuries. Then this is a new one, that's a DLC, the diamond like carbon coating, which will be covered in the next maybe say next to next lecture, lecture 14. And organic materials also can be utilized as solid lubricants, and we have covered this stearic acid um, as a solid, not solid lubricant, as a boundary additives. We generally mix with a liquid lubricant and we treat this as a boundary lubricants, but he has mentioned as a solid lubricant. Of course the polymers also can be treated as a solid lubricant. So this is what and there's a variety of the solid lubricants which are available. So then there's a need to define what is a really solid lubricant, and what definition has been given. The liquid lubricants naturally decrease the frictional resistance. Of course we emphasized earlier that it's not only the frictional resistance, it should also reduce the wear. However, for this completion of definition, I am using the same thing. We say liquid lubricant decreases frictional resistance between relatively moving surfaces that are under load or under heavy load, and is providing the smooth sliding. That means under heavy loaded condition, or maybe tribose surfaces which are subjected to heavy load and having relative motion, if we are providing some liquid and it is really allowing a smooth sliding, then it will be treated as a liquid lubricant. Now same thing, you say any solid substance that fulfills the same purpose can be classified as a solid lubricant. So any substance which provides a smooth gliding to the tribose surfaces, and if it is a solid state, then it will be called as a solid lubricant. Now we also drive the expression related to coefficient of friction, particularly for adhesive joints in lecture 3, and we say that coefficient of friction will depend on the shear stresses, shear stress of the interface and shear stress of the soft matter. And now when we talk about the solid lubricant, we are talking about the tau I. If tau I of the solid lubricant, or maybe it's a solid lubricant which makes interface, and tau I is very low, then it will have some sort of very low coefficient of friction and can be treated as a solid lubrication. Now in that same lecture, lecture 3, we also have provided this table. We say tau I by tau Y. If the tau I is only 1% compared to the soft material shear strength, coefficient of friction can be very low, 0.005. Of course in this abrasive, coefficient of friction has not been counted. Obviously flowing component of coefficient of friction has not been accounted. However, we can say same thing if for the solid lubricant, to have a low coefficient of friction, solid lubricant must possess a low shear strength, and this is a universally accepted. If you want some solid to act as a solid lubricant or act as a lubricant, interfacial shear strength needs to be very low compared to the parent materials or compared to the substrate materials. This is established, and whatever we covered in the lecture 3, same thing is also supported in this lecture 12 also. We are saying earlier we cover only liquid lubricant and somewhat we mix with the boundary additives. That's why we use the word organic materials, and we say the stearic acid which acts as a fatty acid can be utilized as a boundary additives, and then we should go with a mixed lubrication. In mixed lubrication, the surfaces we having asperities, or maybe say rough surfaces having asperities, those impurities should be covered with stearic acid or fatty acid or some sort of boundary additives, so they do not really give a high coefficient of friction in case liquid lubricant is not able to support the load, or maybe it is squeezing out completely. In those situations, the same thing we are repeating here for a solid lubricant. Similar kind of rules, similar kind of principles can also be utilized. So that's a solid lubricant. Now next comes to the solid lubrication process. So we talked earlier in a previous slide about the solid lubricants. Now here we are talking solid lubrication. Say it is a process of introducing thin film. In my earlier lecture also I emphasized that we are moving from thick lubrication to thin lubrication. So in a recent time, or maybe say in the future, we will be talking only about the thin films. We will not be talking about the thick films. Thin film can be maybe say nanometer to micron level. So process of introducing thin films which can be composed of one single solid. We are discussing about the solid lubrication. So it can be composed of a single solid or a combination of the solids also. Sometimes we really require a heterogeneous mixture. We require molybdenum disulfide as well as graphite, or molybdenum disulfide plus oxygen. So these are the combination of the materials can be utilized. um, so process of introducing this thin film composed of single solid or combination of solid between relatively moving surfaces for purpose of reducing friction and wear. So here we are emphasizing it should be reducing friction as well as a wear. It's not only the friction. Of course, obvious question comes, so what is the difference between a boundary lubrication and solid lubrication? There is a thin gap, which is solid lubricant can be capped directly or maybe say and the coated directly on the substrates, while boundary additives generally we mix with a liquid lubricant, and because of the affinity or because of the chemical reaction between those additives and the surface, the film will be formed. While in case of solid lubricant, basically we need to connect or maybe say we need to embed in the surface or coat on the surface. Sometimes we use also as a nano additive, which will be covered in the lecture 15 on a nanotribology. Now to lubricate the substrate is basically the materials which are needs to be and then which are need to bear the load and are under relative motion. We can use anything, we can use organic or inorganic also. However, we know the organic compound they deteriorate the time and maybe in the moisture sensitive also. So at the higher temperature generally we go ahead with inorganic components. So we say use organic or inorganic compounds uh, at the contact or at the interface to minimize wear. Now how do we minimize the wear? We say minimize the deformation, minimize the deterioration or degradation, or minimize the delamination of the surface of the solid material which is getting deposited or coating which we are depositing with that. So that should be minimized. We will be using the word here the dry. Reason being there is no flowability. Like in boundary additives, we think about some sort of flowability of the material. While in case of the solid lubrication, we don't assume there will be any flowability. Can be minimum shear, but flowability will not be accounted as a big reason for that. If it's a boundary additives, yet they can be removed, they can be again reformed. So rupture of the things will happen, or removal of the additive will occur, as well as the again reformation will occur. So dry sliding contact influences the tribal surface tribology based on the material property. Now here we are giving more emphasis on the material properties. Earlier in a previous lecture I mentioned very clearly tribology or tribo interface is a composite system property. It's not a material property. However, the fraction of the material property or dependence of the material property, particularly in a dry lubrication or dry sliding case, will increase because material and material they are coming directly into contact. So viscosity of the lubricant is not there, and mostly the property of the sliding surfaces are coming into the picture. It can be thermal conductivity, it can be the shear stress, it can be hardness, which is the hardness is not a material property, it's a surface property. So many times we do a change or we treat the surface so we get a desirable hardness, which will be also covered in lecture 13 on the surface modification, and then we can really reduce friction and wear by just modifying the surface itself. So friction coefficient in a solid lubrication correlates with the solid lubricant properties. That means whatever we are trying to utilize as a solid lubricant are trying to use a thin film between the two surfaces. Now which mechanism? As I say, there are a number of mechanisms. Even we go with the thin coating or deposition of the thin coating, or we go with the nanoparticles, or we go with the surface treatment. Any treatment can provide a solid lubrication. However, we should know that shear stress or maybe interface shear stress should be as low as possible, and then deterioration of the surface should not happen, or the solid lubricant which we are using, it should not harm the surface. So this is very important. Now why do we really require a solid lubrication? Because in earlier my lectures I say I'll prefer first as a liquid lubricant. It has a number of properties. However, if there is a need to retain the lubricant and we don't want to invest money on the pumps and recirculation system and cleaning or maintenance, then we will go with a semi-solid, that is a grease lubrication. Now here we are talking about the solid lubrication. So preference from my point of view is a liquid lubricant first. If it is not available semi-solid, then come to solid. Now what are the really and the points where the solid lubrication should be selected? We say it is a severe temperature condition. Now in some books you will find a 300 degrees centigrade, some book is 400, some books is a 500. It may vary depend on the substrate which we are using it. Reason being that at the high temperature, liquid lubricant or in the grease, they get oxidized fast. If they get oxidized, naturally they are not fulfilling the function, and deterioration will be faster. And because of oxidation and then some sort of free ions, even the surfaces will also get oxidized or will deteriorate. So there's no point to utilize those liquid lubricant or grease. Similarly, at the high temperature, even this substance decomposed. So if the mineral oil which we are using or additives which we are using, they start decomposing, then there's no point to use those kind of liquid lubricant or grease. Even in case of the cryogenic situation, the low temperature viscosity goes very high, freezing occurs. Naturally in those situations, again we don't really require a liquid lubricant or grease to be utilized. In extremely high pressure, yes, that's also a problem for the liquid lubricant, which will get squeezed out, and then there will not be any lubricant at the interface. And this is a more important what we call environment. When we talk about the high vacuum, the liquid will get vaporized, or it will not be at the surface. Similarly, in aerospace application, we can't use a liquid lubricant, so we use a solid lubricant. What we see, this condition which prevent the use of oil and grease. So whichever the limitation, wherever the oils cannot be used or maybe grease cannot be used, and then preferably we should go for the solid lubrication. So first choice liquid lubrication, second choice semi-solid, that's a grease. And of course the grease has a major advantage of that we don't have to pump again and again, or maybe continuous phase. Liquid lubricant need to be pumped again and again, or maybe splash lubrication also can be utilized, but again there will be some sort of limitation. So we should understand all the limitations of the system and then select the appropriate lubricant. So what are the two primary requirements? We say that solid material must be capable of bearing the applied load, that means it should not squeeze out, and it should not come out, and it should not get deformed substantially. It should not happen that there is a big pit getting formed with the solid lubricant itself, or there is a distortion of this, or maybe say, and then it's getting removed from a surface completely. So those should not happen, that the material should remain intact without deformation. Second thing is that friction coefficient and wear rate must be well within acceptable limit. Again, we are not saying there's zero, because that is a very hypothetical case, zero friction, zero wear. It should be much lower than what the we can think which will unnecessarily harm the surfaces or reduce the service life of the component. If we really required a 5-year life of component and then wear rate gives a 6 years life, then we will not worry about the wear rate at all. And similarly, when coefficient of friction is already 0.01, further reduction of coefficient of friction which causes some fluctuation, there is no point to go out with a fluctuation or say standard deviation is a higher side compared to the mean value. So we will not go for those kind of thing. In this, these are the two primary requirement when we select the solid lubricant. Now further so what else is required now, we say that in literature, particularly if you look at graphite and molybdenum disulfide, they have been covered majorly as a solid lubricant. As I say that there are many solid lubricant, but these two are have been utilized in a very big way, MOS2 and graphite. Now, why the graphite and MS2 generally they have some sort of benzene ring configuration, or we say hexagonal layer configuration, and then this one layer remain intact without any much deformation, while second layer also remain intact, it can bear any kind of load. However, these two layers are connected with weak bonds, and this is what we call a weak van der Waals forces, and this weaker forces allows easy slipping, and then that's why the shear stress or maybe say slipping will be easier. That's why the friction force will be much lower. That's why we say the inorganic solid lubricant with a layered structure, as I mentioned, is a layer 1, layer 2, it can be many layers, and then the layered structure in each layer containing the strong bonds to resist deformation or breakage. So this layer is this layer 1 complete this one layer is solid, it is not going to deform easily, it will not break so easily, and this second layer also same thing. However, between two layers there will be easy sliding, and if there is easy sliding, naturally resistance is lesser, coefficient of friction will come down. And that's now compare when I compare MS2 and graphite, I'll give more votes to the graphite because it has extensively we say the many more features. What are those things? We say this. I'm just quoting the same thing. The benefiting from its vast surface area. So this is a major thing. Graphene, if you take even a small weight, its surface area is very high, and in tribology we are more prone to the surface area. We say that we really record big surface area, lesser volume, and everything is a 2D kind of thing, and then if the surface area is more, we record a much lesser quantity of the graphene. Even sometimes we record only 0.05%, and then it really gives a good results. If I go with a 0.5%, it may give bad results. So this is interesting thing. If I use a more graphene, more layers, it many times gives a higher coefficient of friction compared to the lesser quantity. So this is a vast surface area, and one more thing is exceptionally high thermal conductivity. It doesn't allow temperature to rise. Whatever the heat generation, it really immediately dissipate the heat. This is a very strong point of the graphene. It dissipates the heat much faster. It doesn't accumulate the heat there, and because of that, this a solid lubricant can be very good. So that's why we say graphene sheet is very efficient in reducing wear and friction by forming thin lubricant at the interface of the contacting surfaces. Now, one layer, two layer, three layer, okay, but if you go with a 50 layer, 100 layer, again there will be some sort of bulging, some sort of crumpling, and that will increase the coefficient of friction. That's why I say that quite possible 0.05% of the graphene, when we mix the nano additives in lubricant, quite possible the results will be much favorable compared to the higher percentage. So it needs to be really checked appropriately. And here, whether MOS2 or graphite or graphene, they have intermolecular on the bond, that's the pi interaction. That's but we are using the word here, we already shown the benzene ring configuration, and then you see interaction are because between the two layers, interaction are basically van der Waals forces, and then it is happening because of the overlapping of pi electron cloud, and this pi interaction causes a lesser shear stress, and that's a weaker bond compared to other bond, like we say we use the word hydrogen bonding, or we have already known about ionic interaction like NaCl or something like that. So where the ionic bonds are there, which are much stronger. Even hydrogen bonding is much stronger. So shear stress in those cases will be on higher side, while in case of the graphite and molybdenum disulfide, whether the benzene ring, and then there is and the van der Waals force between the layers, the coefficient of friction will be lower. Of course, it is not only this, there are many materials, similar materials, but graphite has turned out to be, or graphene has turned out to be much more popular compared to other material. And one of the good thing about the graphite material is that it is not really harming the environment. That's a very good aspect, or maybe say the good feature of the graphene. Now we referred the tribology handbook because we need to pick up the data from literature, and then graphene. Then this tribology book says, why do I talk about the solid lubricant? Why not we treat this whole material as a solid lubricant itself? So what I'm trying to convey here, there is a substrate 1 here, substrate 2 here, and now if I'm using this as a thick solid lubricant, instead of that, why not I make us 2 as a solid lubricant or 1 as a solid lubricant, complete material. So that's what we are using here. But properties of the typical dry rubbing bearing materials. We know that bearing materials means it needs to provide a lesser coefficient of friction, it should support the load, it should have a minimum wear rate also. So these are important, and this Niels book, they have divided solid lubricant of the bearing material as a thermoplastic, which acts as a solid lubricant, thermoplastic with the fillers, PTFE with the fillers, high temperature polymers with the fillers, thermoset with the filler. You can see here every time we are using the word fillers because we are not satisfied with the basic polymers. We want to increase the properties or even improve the properties of the those fillers and those polymers with the filler. Here carbon graphite, which we have used also for one of the carbon graphite seal, which was required for the steam environment. Carbon metal, now soft metal we also use extensively, and of course it has been utilized for the ages. Now it was utilized, and people start thinking about polymers are giving better result. Now we are becoming back to the soft metal because we require a better processing, because soft metal have a self-healing properties which are not available in other metals or other polymers or in the graphene kind of materials, because self-healing is more in soft metals. When the micro cracks which gets developed, and then after that if there is a some sort of hot spot coming, it really builds that crack. So there is a self-healing properties in soft metals that will be also covered. You can see here they have provided what should be the maximum static load, and then in previous lecture we covered 10 megapascal as a one of the constant in a bearing design, and then this is a what has been given for thermoplastic. Now that will further come down, instead of 10 now it's a 2 to 7 when we are using PTFE. So many times people immediately say, oh, we use PTFE, but we should know that it has a much lesser properties compared to other material. If the load carrying capacity is enormous requirement, then we cannot use a PTF even with the fillers. Even the carbon graphite, again we cannot use as it is, because one of the seal which we use this antimony, almost 30% antimony in that to improve the properties. So these are the important aspects. Carbon material, again here my strength is much lower side. So another one is that the expansion coefficient. We say that we should have a high static limit, we should have a low coefficient of expansion. If the coefficient of expansion is lesser, the delamination chances will be slightly lesser, or separation of the lubricant layer or solid lubricant layer will be lesser. So those things are important. And one more thing is the thermal conductivity. As I say, carbon graphite can have, so the graphene can have up to 5000 as a thermal conductivity. So it is very important that will be level requirement. Like in we know the polymer has a low heat conductivity. You can see 0.24, 0.24, 0.25, and then this 0.37, 0.3 to 0.7, thermostat 0.4. Coming to carbon graphite 10 to 15, 15 to 30. Coming to metal is a 50 to 100. Now graphene will have a more than this metal itself, and we really require a good thermal conductivity, and graphene provides much better than metal itself. So it is very important, and we should count those things. However, even the Niels book has covered a number of materials which can act as a solid lubricant, because we make complete as a solid lubricant in bearing as such. The material which has not been accounted in molybdenum disulfide. Now this is a turning out to be very good material, which we have also experiment on this is a hexagonal boron nitride HBN. This is a very good material, and many times it gives a better performance compared to the graphene in different environment. As I was discussing about the soft metal, if we have a proper science, we can utilize soft metal in a much higher level, obviously better properties. Reason being, the soft metal also has a low wear rate compared to other materials. So even though we are sacrificing to some extent the coefficient of friction, but we are gaining importance on the wear. So what is really our requirement? Is that the lowest friction or lowest wear, or a combination of this? And in previous lecture I mentioned that whenever there is two systems, so when we require a minimum wear and we require a minimum friction, we should use appropriate technique or appropriate optimization technique, or we use a multifunctional in the optimization. That will be important. We should utilize those kind of techniques. Of course, in this case we are talking about the diamond like a carbon coating, which will be covered in next lecture, that's a lecture 14. And we reason being, those coating really required advanced manufacturing coatings or techniques. In this case, we are using the word advanced vacuum deposition processes. So we really require more manufacturing, or better manufacturing, to deposit those layers on the surface. So this is a very sophisticated, and we deposit the layer of the few microns, which can really last for the 10 years or so. So this is very important, we should learn, and that will be in lecture 14, not next lecture, lecture 14. Next lecture is surface modification. Now this is what is being shown here. You can see material strength for the material is 350 700 megapascal, very high requirement in this case. Coming to the maximum temperature, thermoplastic, any polymers related, you can see the temperature is 100 150. Well, if we are increasing the thermal conductivity, then temperature, maximum temperature subjection is around 250. Here you can see it is heat conductivity 0.37 to 0.3 to 0.7. Again, the operating temperature can, maximum temperature can go up to 250. Coming to the thermal conductivity 10 to 50, here you can see the maximum temperature can go up to 500. So that's what I say, that whenever you are going with a material and you say now above 100, above 150, above 200, above 300, materials need to be changed according to that. Now if thermal conductivity is on higher side, temperature on the will be maximum temperature, permissible maximum temperature will be on a higher side. So that is what we really keep in mind. Now these data are available in literature, only interpretation, inference of those data and utilization of those data are important. How do we utilize for the maximum benefit for our purpose? Now most of the publication of books, they talk about only the friction, coefficient of friction point of view, whenever they discover the solid lubricant. But here the Niels book also provides a wear rate. You can see the wear rate has been given in mm cube per Newton meter. Some books they refer, instead of mm cube, they say the meter square per Newton. So it is the same, only the unit may change. When we are talking about mm cube per Newton meter, that's indicating 10 to minus 6. While if we use this unit, naturally 10 to minus 6 and minus 9 also will come. So it will turn out to be 10 to minus 15. So this is what we really require to keep in mind. The dimensions should match, and the coefficient of friction, coefficient of wear, whichever we are tracking or wear rate whichever we are using, that should be accounted. And earlier slide I mentioned very clearly, this is a specific wear rate where the hardness has also been accounted. We don't separately account the hardness. Here hardness is already inbuilt in this case, so that is a possible. Now again in this case we can see that unfilled PTFE wear rate is very high. Unfilled thermoplastic metal plus solid lubricant, the wear rate is coming around 10 is to minus 6. Then we have a laser, of course, a bonded solid lubricant film. That's what we say. The coating we will go ahead. They have a low wear rate, and then of course porous material. They also have a low wear rate. Reason being the material or liquid lubricant is already there embedded, which may run for the 10,000 hours, and after that we can replenish it or we can change it. So those things are important. Now sometime we say that this we are not happy with this material wear rate, we want to reduce this. How can we reduce? If you go for the bimetallic bearing or trimetallic bearing, that's possible. What is the reason? That whatever the base material, like in this case is steel, and if on the top we are using copper, then we are using intermediate layer to the and the doesn't allow ingress of the water or oxygen, and then also provide sufficient support, and this is the bearing material or solid material on the top. That means it can be a soft metal, it can be any other solid lubricant metal on the surface. If you go for this kind of a trimetallic coating, a bimetallic coating, that gives a good strength or the much lesser wear rate compared to what has been quoted here. So more and more research people are doing, and that give this kind of data will keep changing. Now today we are talking about a wear rate 10 is to minus 6, this mmq per Newton meter. Maybe quite possible after 10 years we will be talking about 10 is to minus 15 mmq per Newton meter. So there is a possibility. And then whenever we are talking about this kind of a trimetallic or bimetallic coating, we need to think about the thickness. We say thickness should vary from few nanometer to few micrometer, should not vary. Then it should not go in mm. Of course, in few books it has been mentioned it can go to 3 mm, 4 mm also, but lower thickness will be more important. Reason being, a lesser the thickness, and base material thermal conductivity will come into the picture. If you go for thicker coating and solid lubricant material, most often they don't have a good thermal conductivity. In the situation, the heat dissipation will not be very effective. Localized welding will occur, coefficient of friction will increase. So that's why we are writing here the reduced wall thickness to enhance the heat dissipation. We should not go for unnecessary thicker coating. We should dissipate the plan in a manner the heat dissipation should be effective. One more thing is that when we are talking about the polymers, polymer has a problem of the moisture absorption. Now if there is a in the environment and which is there is more chances of the absorption, we should not use this kind of polymers. So that's why I say that if we are using, we need to account the dimensional changes. What will be the dimensional changes if we are trying to keep it, what will be the final tolerances, and that will be affected by moisture absorption, even the expansion of coefficient. If the heat generation is a higher side and it has a high expansion coefficient, naturally the tolerances will change. Sometimes stress relaxation also occurs, whatever we are doing a surface treatment, and then we are allowing it to operate in tribo situations, and then under stress relaxation the dimensional changes will occur. So we need to give more emphasis that whatever we are doing, we are choosing a right material, we are trying to do everything right, but if we are not accounting this, how much dimensional changes will occur and how much reduction in clearance or increase in interference will occur, then it will not give a satisfactory results. One more thing has been given here. We are talking about the bimetallic or trimetallic bearing. Here we are talking about some sort of the bronze bearing, and which has a number of holes, and in this can we can we say the embedded graphene from aluminum disulfide, those things can be embedded. So here the bronze itself was working as initially the bearing, and now we are using the liquid lubricant or maybe say semi solid lubricant, or we are using the solid lubricant here. Particularly in this case we are using a solid lubricant. Now this bearings also can be made of porous bearings, and in porous we can really increase the liquid lubricant also, so it will give a very good result. So that's why I'm mentioning that more and more technologies are coming and upgrading the bearing technology. So initially we were using only bronze bearing. Now the porous bearing which have an impregnation with liquid lubricant, or it can be grease also. And here we are showing a picture of the carbon graphite and which has been embedded in this kind of holes. So those things will really change the bearing characteristics. So whenever we do a literature review, we should keep updating ourselves that what are the really the right properties which should be accounted for the design purpose or application purpose. One more thing which I picked up from this Niels book is something like environment, and environmental facts are very significant. You can see here the carbon graphite, it gives a good results at the high temperature, and then even the low temperature also. And then coming to the radiation also, it is okay. Only thing is that we should not use a resin. Now, particularly vacuum case, it becomes useless. We should never ever use a carbon graphite when if there is a vacuum or low pressure case. And it gives a good result in water. Of course, I will show you the one case study. If you use excessive water, then again is a bad. So there should be water and there should not be excessive water. These are important aspects. Coming to the incomes of the abrasive, because material this carbon graphite do not have a good strength. So whenever there is abrasive material, it will perform badly. So this is also important. Coming to the graphite, coming to the polymer side, you can see they don't work very well in terms of radiation. They deteriorate very fast, all polymers. So if there is a radiation environment and we are using polymers, with the time they will really change the shape, and then we say that if properties also will be changed. So there's no point to utilize, and if you are utilizing, then it should be short term, it should not be the long term. Another one, in the presence of water, as a graphite, carbon graphite is giving very good results, but in the presence of water, polymer will not give good results. So this is a very important. Of course, abrasive case, again they don't have a good properties to resist the abrasion. Actually, it will not really show the good performance. So what we are trying to summarize this way, we say dry lubrication, because reason being we earlier covered Tribeca, and we share that there is a hydrodynamic lubrication, mixed lubrication, asperity contact, and asperity contact is basically dry lubrication. That's why I have written here, often termed as a dry film lubricant. And earlier in this case, particularly the mixed lubrication, we say that there are two type of lubrication. We mention about the boundary and thin film. And in the present lecture, I try to give explanation what is the difference between boundary lubricant and a solid lubricant. That's important. And then we talk about the thin film, as I mentioned earlier, that we don't talk in these days about hydrodynamic film. This film is will not be talk of hydrodynamic lubrication, but portion whatever 70% 80% comes, so it will not be absolute or completely hydrodynamic, it will be thin lubrication. Reason being, we are talking about the this zone which gives a minimum friction and minimum wear, no compromise. We can say the zero wear, but we are compromising on the friction loss. That is not correct. We want minimum friction, minimum wear. Again, there will be finite value, it is not a zero value, but we need to optimize according to that. So that's why we see that the process of boundary lubrication, bonding this basically semi-solid film to the each surface, liquid lubricant will flow, and this boundary lubricant will get attached to surface and can be detached also. So adsorption, desorption, or maybe simultaneous also. So this is where the attachment and detachment is possible. Coming to the thin lubrication, particularly we know the viscosity will impact, and then in this case liquid will not get attached to the surface. So there will not be attachment to surface, and the attachment to surface will happen because of the boundary additives, boundary lubricants. However, if we are going for solid lubrication, then solid lubricant layer need to be attached to the surface. Now I given another example that there is a possibility that we use solid lubricant like MOS2, like of carbon graphite, as a nanoparticles into liquid lubricant. So in that situation, it may be treated as a solid lubricant or may be treated as a bonded lubricant. So there is a thin layer between these two, and we don't have a much. Of course, we use a word a specific film thickness. We say specific film thickness is 0, then we can think about a solid lubricant, and a specific film thickness greater than 0, lesser than 1, then it can be treated as a bonded lubricant. That's a one way to divide it. But again, this H minimum What is the meaning of this? If I'm assuming everything, we say the surface, the RMS of surface 1 and RMS of the surface 2, right? So in this situation, what is the meaning of H minimum? Solid lubricant, if I am depositing a few micron, and we know the surface roughness can be calculated, I can calculate this specific film thickness even for the solid lubricant, because we are going to deposit the coating or deposit the film, or maybe say even level. Naturally two surfaces are getting separated, and there will not be trying to reduce the wear to low level. That should be accounted. Now, we discussed something of environment in a previous slide. Now I'm continuing it. We see every lubrication on the lubricant may be slightly different in lubricant in the case of the environment, and I'm trying to give example over here. We say water vapor is a necessary to reduce the coefficient of friction for the graphite, but it really is a hampering the MOS2. So it is not really supporting the properties of MOS2 in presence of the moisture. MOS2 will not be working very nicely. So same thing in the MOS2 as well as the WS2 also, right? So unlike MOS2 and WS2, graphite needs some moisture or adsorb gases to, we say that there is a covalent bond, and then we need to passivate that covalent bond, so that acts as a good lubricant. So if there is a covalent dangling on the bond, or the bond which happens in this graphite or graphene or graphite, then we need to really passivate that bond, otherwise it will coefficient of friction will be on the higher side, and in an absence of moisture, this bond cannot be passivated, and then maybe coefficient of friction will increase. And now this is, has been mentioned, we say in vacuum and dry environment, graphite without any other additives, water is one of the additive, exhibit high friction, and in 1930 this phenomena was observed, particularly in the brushes, graphite brushes, where the wear occurred accelerated manner. In 1930 there was a casualty, and then this carbon brushes, they really gone through the accelerated wear, and then they later realized that their this sliding properties or lubricating properties of carbon graphite cannot be utilized in the absence of moisture, and then the name was given as a dusting. That means it will turn out to be like a dust form, or maybe powder will keep coming, and wear out will be much faster. So that's important. That's why we are saying that in different environment, different kind of solid lubricant can be selected. While in this case graphite cannot be selected, but MOS2 can be selected in a very nice manner. Even in previous slide we mentioned about some sort of polymers can be utilized, but again the temperature is on hard side, then polymers cannot be utilized, only MOS2 will be utilized. One more problem comes in a solid lubricant, particularly bulging of the film, or what we call is this kind of a blistering of this film. If the film is not smooth and there is some sort of blister formation, then the deterioration of the solid lubrication will be much faster, and we should not either we do a good coating, or when we are mixing the this as a nano lubricant or nanoparticle in liquid lubricant, then we need to make sure that there is no much abrasive particles or other impurities in that. The way we have discussed about MOS2, WS2 and graphite, similarly is HPN. And then this now is getting more popular, because we know that this gives a very low coefficient of friction, and many times even compared to graphene it gives a lower coefficient of friction. So HBN can be utilized as one of the solid lubricant. I'm just trying to cover one case study on this solid lubricant which is related to the carbon graphite. Yeah, you can see the whole carbon this solid lubricant had been used as as a seal. So this is a secondary seal, and this is the primary seal, and this secondary seal has been utilized in here in a steam joint, and primary seal on this case here. Basic purpose is to avoid the leakage of steam, and when to avoid the leakage of steam, naturally they need to have a very firm connection with the shaft. And what is the shaft? This is the shaft here, stainless steel shaft. It needs to have very close tolerance connection, and when there is a close tolerance connection, naturally wear rate will be high, friction will be high. So that's why we use a carbon graphite seal. Now what happens to carbon graphite? Initially layer will be transferred. So this is a very major point to discussion, that here the carbon graphite layer gets transferred to the shaft. You can see without layer, any layer. Now here there is a carbon graphite layer, and this bridges the gap. This transfer of the carbon graphite layer bridges the gap, and then steam is unable to pass out. And here the steam environment acts as a lubricant for along with the carbon graphite. Or in other words, the carbon graphite works much better manner in presence of the moisture or in presence of the vapor, water vapor. And that's what the good solution comes from this. So of course, if you apply more pressure, much higher pressure, because we know the carbon graphite cannot sustain high pressure, and if you apply more pressure, then you can see that more burning is happening, or wear it is much faster. So one thing is that if you apply more pressure from back end, maybe say in this from back end side, so that this comes, and if I apply more pressure from this side, and then there's a more interface happens over here, coefficient of friction will increase, wear rate will increase. So it has to be controlled properly. So we also try to experiment within the two situations. One thing is that whenever the this paper industry, they work with a steam environment and they shut down, so we assume that if they are shutting down, what is the level of the water which remains in this joint. If the water level remains on a higher side, we find the carbon graphite continuously get dissolved in the situation. And then if water level remains much lower level, we observe that carbon graphite doesn't dissolve so fast. And this is a very important aspect, that we want some moisture but not very high moisture. On a high level of moisture, where it will be very high. So that's why we say maximum seal wear occurs under complete water environment. That's what has been shown here. If I'm operating this turbine, or we say the paper mill, vapor gets evaporated from a pulp paper, and then when we stop a steam boiler, and then suppose water level remains on a higher side at the steam joint, in this situation the wear rate will be very high compared to the lower side, this side, and this kind of case. So minimum wear occurs under water lubrication or vapor lubrication, which happens in this situation. Even the low level there will be water, and it get evaporated little bit, and then it will be able to provide some sufficient lubrication to the carbon graphite surfaces. Now, when we talk about the dry bearing, naturally we have discussed something about a high pressure or high velocity or high temperature. So there is some sort of mathematical relation what we use many times, a PV factor, or sometimes we use the word mu PV factor. That mu is a coefficient of friction and pressure and velocity. So this, what is the meaning of PV? We say that there is a graph for every this solid lubricant case. We can apply maximum load up to one limit. Beyond that, wear rate will be much faster, and then we can apply velocity, or we can rotate up to one's velocity. Beyond that, wear rate will be very high. And then there is a in this case particularly, this much velocity, but in the pressure remain this remains constant. After that, there is a taper, or there is a decrease in this limit, so what we call a PV limit, and after that the stop happens. So this is what overall curve indicates, and we need to operate the bearing, or maybe it's a solid lubricant, in this region only. So that's why we say the limiting PV, which we above, if we go above PV limit, then wear rate will increase rapidly, and then reason being the temperature increase will be significant in this case. How do we calculate the volume of wear? Is very clear that we can multiply with a specific wear rate which is available for materials, apply load and the sliding distance, how much is sliding distance. Same we can use earlier wear law which we have derived in lecture 3. Here we can find out the specific wear rate or wear coefficient into the load into the distance. If you want to divide by area, then wear at one dimension h can be given this terms on this relation. So here we are adding new term that's called energy dissipation, which we not discuss earlier. So we are adding this one. We say area of the heat flow, projected area can be given. Of course, this is an elementary calculation. When we go for detailed analysis, we need to really come up with the right results, right area, and then friction force can be given into mu into W, which we know the mu doesn't have any meaning as such, because at a various junction the mu can change also. And overall power loss is generally the frictional force into velocity. And energy dissipation per unit area, when we divide this FV divided by A, then it will turn out to be mu PV, and this is the same thing which I mentioned over here, mu PV. So just to understand it, I'm just picking up one example here. We say estimate wear rate of a 10 mm long bushing, 10 mm diameter, 5 kg weight of the shaft, and it is rotating at the 900 rpm. Now, material for the this solid material is being given as a nylon material, because nylon acts as a solid lubricant material. Maximum temperature which can operate up to 90 degree. Now PV limit, as I mentioned, P into V, it has been given as a zero point 0.9 mega Newton per meter per second. And individual pressure, maximum pressure, that's here it is given the 5 megapascal. Velocity has been given as a 3, instead of rotation here we say the 3 meter per second. So this has been given as a limit. So what we do calculation. Simply we define what is the length, what is the diameter, what is the load or W, and what is the rotational speed. Operational, this V has been calculated, P has been calculated. We know the maximum value of V max is 3, the maximum value of P is 5, and PV limit, if we calculate the values, we know the diameter 10 mm, length 10 mm, rpm 900, pressure is overall what we have calculated coming around 0.49 megapascal, and PV limit which we have calculated is coming around 0.23, and available is a zero point 0.9, and the velocity 0.47, available as up to 3, and then load is being given here. That means in this, if we want to really test this bearing, it is fine. So 10 mm long bearing, 10 mm the shaft diameter, and then it can sustain a 5 kg load which is running at the 900 rpm without much failure. This is a indication that from a line point of view it will be okay. Now if you want to calculate the wear rate, naturally the nylon has been given as a 4 no filler, that can be calculated. So when we use this 4 into 10 is to minus 15, here earlier as I mentioned that 10 is to minus 6, um, this mm cube per meter, and now if you multiply with the 10 is to minus, when the sum of 10 is to minus 9, that will turn out to be 10 is to minus 15. So this is what has been given for nylon. This is the load and this is the velocity. So wear rate is coming something like a 9.22 10 is to minus 14 meter per second. It's per unit second, this much loss will happen. Now if somebody wants to operate for 1000 hours, then we know very well the clearance of the bearing will increase significantly, and this cannot run at that this one. No, why we are saying here, because here this is the wear rate, the V by T, right? So 9.22 into 10 to minus 14. Now if I had to bring T over here, naturally the T can be calculated like 1000 hours into 60,000 minutes, and RPM is 900. So this multiply should come, and then what will be the wear rate, whether this wear rate is acceptable or not. If it is acceptable, it's okay, because in this case 1 mm the bearing diameter is getting removed, 1 mm radius is getting removed after 1000 hours. Naturally bearing will not act as a bearing, and then the wear rate will be very high. And in the situation, one more point will come, that whatever we are assuming K as a constant cannot be remain constant, because initially the bearing was a whole surface, and then load carrying capacity was on higher side. If the wear rate in much faster pace, then we will say that load carrying capacity is decreased significantly. In the situation also value of K will increase. So quite possible no filler case will be rejected, and we need to move to the filler case, which is really decreasing wear rate significantly from 4 to 0.24. that need to be accounted. So what we can say, what we have discussed about the characteristics of the solid lubricant, we say that low shear strength is required very essentially. Again, we are saying only low shear strength is not sufficient, but addition to the surface is also required. It should not happen that you have low shear strength of the material, but if it doesn't stitch to the surface, doesn't get bonded to the surface, then it is not really a good lubricant. So both the things, attachment to the surface is required, low shear strength is also required. On top of that, the when previous slide as I mentioned, there will be wear rate. So that wear rate also need to be accounted. So again the tribology is becoming the time dependent. Whatever I have designed initially may not be okay for the after 10 hours or 15 hours or 100 hours. That need to be checked, because if a lubricant wear is going to move away, wear it will be there. That's why many times we say the liquid lubricants are far better. But if conditions are not permitting, environment is not permitting, the solid lubricant, then we should evaluate after 100 hours what will be the life, after 1500 hours what will be the life. Again we see another solid lubricant is a molybdenum disulfide. If it is operated at a higher temperature, sometimes we say the 300 350 or the temperature, then the whole this MOS2 also get decomposed, and then there is a possibility of generation of hydrogen sulfide, and it also another problem comes hydrogen embrittlement. So MOS2 is supposed to work as a good solid lubricant, but it can create a hydrogen embrittlement which increases the wear rate significantly. Second thing about requirement is basically the solid lubricant, it should not act abrasive material, because we have recently observed graphene, if you use in excessive quantity, they crumple and then make and then they increase the wear rate. So they act as a solid an abrasive material. So we need to also keep in the on the check on that, that it should not have a high abrasiveness, or another word we say lubricant particle must possess a lower hardness than the bearing material, because we know that if this hardness is lesser than zero point 0.8 into the hardness of the bearing material, and the hardness of the bearing material, then where it will not occur, abrasiveness will not occur. So in other word, if the 80% the hardness of this materials which we are choosing, they are lesser than 80% of the bearing hardness, software bearing material hardness, then it's okay. Otherwise there will be chances of the abrasive material, abrasive wear. One more, as I mentioned here, the molybdenum disulfide decompose. So we need to keep and to check that thermodynamic stability of the solid lubricants remain intact, and they are really applicable, suitable for high temperature application. Otherwise, it will not be act as a solid lubricant. It should also remain in storage stable condition, should not get corroded. Few materials get corroded, and in presence of moisture they get also oxidized at temperature, they get oxidized. So that should not be there. One more thing which is very essential is the self healing mechanism, which I mentioned, that most of the time the soft metal, they have a self healing mechanism, but other lubricant generally they do not have. So this is a very important aspect. One more point comes as synergetic effect. If I'm using solid lubricant as well as a liquid lubricant, then there should be synergy. It should not happen that liquid lubricant is reacting with a solid lubricant, or solid lubricant is reacting with a liquid lubricant. So these are the important aspects. One more point, we say that we should go with a thin coating. Thin coating is very important, because when you go for the thick coating, what will happen, that most of the time the support substrate will not play much role, and then this thick material will play more role. It will get deformed, it will cause a more wear and cause a more friction also. So as far as possible, whenever we are using solid lubricant, they should be used for the thin layer coating. It should not be utilized in a thick form, in form, which was earlier cases. Previously people used to use a bearing of the thick metal bearing as such, Now it's always a bimetallic or trimetallic, or we are doing some sort of conditioning on the top surface, or we are doing some sort of a surface heat treatment so that good lubricant layer or coefficient of friction can be reduced to significant levels. So this is very important. And of course we say of in the future we will be thinking about a 1 micron coating, but it depends on the surface roughness also. If you are able to keep surface roughness in nanometer level, then it's okay, or if you are able to keep more area of contact, then it's good. Otherwise this thickness can be increased to 15 micron to 20 micron also. Now this again I'm bringing from Neil's handbook. We say that solid lubricant is kind of the summary of the solid lubricant. When liquid lubricant become undesirable, ineffective, then we really require a solid lubricant. When they will liquid lubricant will become undesirable in any contaminated situation, like in a food industry, electrical context, we can't use this liquid lubricant. So we use the solid lubricant. Storage problems, we can't use a liquid lubricant, becomes important for us. Even in case of the corrosive gases, we can't use it. So even when we say that different kind of reactivity of the environment, we can't use a liquid lubricant, we can't use in vacuum situation, we can't use in extreme pressure situation, we can't use liquid lubricant in cryogenic situation. So this is a kind of summary whatever we have mentioned earlier. Again this have been divided in four domain. One is a lamellar solid, one polymer solid, other one is soft metals and oxide. However, sometimes people have used ceramic as a coating, separate coating also instead of oxide. So depends on the different kind of authors here. Neil has divided in these four categories, and I find this also very good. And I also mentioned that this soft metal, they when they get heated during rubbing, because the hot spots will come, and then they can really bridge the some sort of cracks. So self healing properties of the this material have, and that should be utilized. However, there are a few disadvantages of the solid lubricant. As I say, the one of the major disadvantages is poor self healing, poor heat dissipation, and then higher coefficient of friction compared to liquid lubricants. So this solid materials can handle it easily. If you go for the thin coating, where poor heat dissipation can be accommodated easily. Again, when we go with the thin lubrication and then low coefficient and maybe very good surface roughness, then this high coefficient of friction and high wear rate can be reduced, can be controlled also. So that's also important, and we can handle it easily. So try to, as I'm giving them more again advantages coming from soft metal, because they have a very good wear life, even though slightly higher coefficient of friction, but good wear life. Now question comes whether we want extremely low coefficient of friction, or we want some sort of justification low coefficient of friction as well as low wear rate. So if there is a low wear rate is also one of the major requirement, then I'll prefer to go ahead with the soft metal, because one of the estimations says that if you use a soft metal coating, then almost a 20% life of the component can be increased without much problem. So this is very important. And another thing is that soft metal, they don't work with the transfer of the layer easily. However, they work with sort of this low shear stress. The coefficient of friction will be on a higher side. There are some material like tin and indium, and they get damaged with the chemicals, so we need to really see which materials will get damaged. And that's why in these days people are using more silver and gold. If you look at the number of electronic devices, they use a silver and a gold as one of the material in this case. So that's very important. When coming to the very high temperature situation, and then we can use the ceramics, but when we require slightly lesser, then we can think about a cermet as a temperature and the material which has the good toughness and ductility also. So we have covered soft metal, but now soft metal also have a number of variations. It can add some sort of ceramics and the metal, which makes a cermet material as one of the solid lubricant material. Now probably these are the last slides. This we say that we already covered the biometallic coating. We say basically we use the word duplex coating for this. Reason being, there's a material, sub material, there's a coating, and in between there is a layer also, and that is a substrate, intermediate layer, and hard coating on the top. This intermediate layer sometimes is a nickel or cobalt coating. They increase the toughness and they increase the resistance to corrosion and oxidation. So earlier these all informations were not given. People used to think, oh, polymer coating is the best coating, ceramic coating is the best coating, but now there's a lot of research has happened, and we say we can really design a coating for our purpose and can get a good results on that. So this is what we've been mentioned. The duplex coating also can provide a good results, and with this I say thank you for attending this lecture. Thank you.